All right, this is the discussion of 2001 past paper. So the questions that we'll be discussing will be (22, 23, 35, 39, 48, 50, 51, 54, 55, 59, and 60. Right, so we start with question number 22. An object of mass simple m is hung by a string and is kept in equilibrium as shown in the diagram by a horizontal force F. The magnitude of F is, right. So this is a simple equilibrium question. So we have three forces. The forces I will mark, and there's a tension, weight, and F force. Right, so what we can do is we can resolve the system through two directions, horizontally and vertically. So when you resolve it vertically, it will be T cos theta equals to mg. This is what you'll be getting when you resolve it vertically. And when you resolve it horizontally, you'll be getting F is equal to T sine theta. So we can divide the two equations, T sine theta over T cos theta. T sine theta divided by T cos theta is equal to F over mc. You'll be getting that F is equal to mg tan theta. The first answer. Question number 23, right. So this is a very easy question if you think in the proper concept, if you use the proper concept. Hari concept එක පාවිච්චි කරොත් මේක ගොඩක් lazy ප්‍රශ්නයක්, right? හැබැයි මේක ගොඩක් අය misunderstand කරගන්නවා moment sector, right? You think about a balance where the balance works with the concept of moments, but this is not moments. Make a moments question. This is just equilibrium question of forces, right? So why do you don't get a proper answer for this? Because you think of in terms of moments, right? So what we have are two masses attached to a light inextensible string passing over a smooth pulley. You know, if you have a smooth pulley, what will happen is that there is no tension in the string. There are no different tensions in the string. There will be only one tension in the string, right? So the forces acting on this system, you can mark them like this. The tension is the same. You can also mark forces on the pulley. They are also tension forces. And the weights of both of them, A and B, seem to be equal, right? So what you can think of this is there's no resultant force. The system is in equilibrium, right? So you can say the system is in equilibrium. The system is in equilibrium. So there's no acceleration, right? No acceleration. There's no acceleration. System is in equilibrium, so there's no acceleration, right? So the mass B is now moved down. So you're moving mass B a little bit downwards. So I can mark it like this. Now mass B is below and mass A is above. Now when you mark forces to this system, still what you can see is there is no resultant force. It's W towards this side and W towards this side. So there's no resultant force. Okay, resultant force එකක් දැනුත් නැහැ. So what will happen? It will stay there. Nothing else will happen, right? If you think that these masses will come back to the original position, that means you're thinking in terms of moments in a balance of Faraday but this is not something like that, right? The forces are equal opposite. So once you keep it somewhere, it will stay there because this is stable, the neutral equilibrium position, not stable or unstable. It's the neutral equilibrium position, right? So B will stay stationary. Nothing else will happen, right? Question number 35 refers to vertical circular motion. So there's a swing, and there's a child, the swing, attached to pivoting points with two ropes, each length of 3 meters. So we can mark the forces here. There's an mg mass, that's being given 200 newtons, and there'll be tensions on the rope. We assume them to be equal, right? So the child is moving at the lowest position with a speed of 3 meters per second. So how do you know that this is the lowest position? They say the maximum speed of the child during the swing is found to be 3 meters per second. So this is the lowest position. This is the lowest position. This refers to the lowest position because the maximum velocity we have is where the lowest position is. Lowest position is maximum velocity, maximum speed, right? Okay. So what we can do is we can apply F equals ma towards the center or upwards, let's say. So the force acting upward is 30, downward is 200, also needs to support. Now 30 minus 200 is the centripetal force which supports the motion. Mass is 20 kilograms. V squared, that is 9 over R radius. Radius they have given as 3 meters, where I have not marked. So better mark it now. In the diagram, all the data should be there. If not, you don't call it a diagram. So 3. So the equation that I used is V squared over R. mv squared over R. Centripetal force equation, right? So when you simplify, you get 130 newtons per tension. That's the first answer. In question number 39, they have explained us that there's a rocket which moves with an acceleration of to the vertical direction with 2 meters per square second. And in that, there's a tank filled of liquid oxygen, which has a cross section of 3 square meters, and also has a liquid oxygen of 1.8 into 10 to the power 4 kilograms. And they're asking at the liftoff, what is the pressure acting on the surface, bottom surface of the tank, right? So in order to find it out, we have to find out the normal reaction force given by the liquid, the tank on the liquid oxygen, right? So in order to find this out, we have to apply F equals ma. We're applying F equals ma upwards to oxygen. So the upward force is R minus downward force is its weight 1.8 into 10 to the power 5 equals 1.8 into 10 to the power 5 into 2. Which actually is correct for 10 to the power 4. So you get is 7.2 into 10 to the power 4 newtons. And in order to find pressure, we have to divide the force or the area by the area. So the force is 7.2 acting on the surface as well. And area is 3. So what you get is, oh, this is not 7.2. There was a small mistake. This value is not 7.2. This is 21.6. 21.6 into 10 to the power 4. And once you divide by 3, what you get is 7.2. 7.2 into 10 to the power 4 newtons per square meter, or essentially Pascal. So it's the fifth answer here. So if you wonder how to start this question, the way that you need to start this question is that you have to first figure out, in order to find pressure on this surface, you have to find the force acting on the surface. That force acting on the surface is this R. Right? I have not marked the required force here. On a force second mark reaction again, so we have to mark this force as well. I did not mark it because I didn't have space here, but we actually call this force is not this one, but the reaction of it acting on the surface of the vessel. Right. Question number 48 is a typical potentiometer type question. So we have been given 2 cells and 3 resistors and 1 ammeter here. And I'll tell you which part of the circuit works as the potentiometer's main circuit, this part. This is the potentiometer's main circuit. They are asking the value for this R so that the ammeter reads 0 current. So there is no current in the ammeter, no current, right? We can mark it first that there is no current. So the only part in which that we have a current is this part. So there will be an I current in this part. So we can mark it there. So if there is no current in this whole part, sampurna part ke current ekak naththam, there is no potential difference between the ammeter and the resistor. Ammeter ekai resistor ekai athara potential difference ekak naha. According to V equals IR, when I is 0, whatever the R that you have, V is going to be 0, right? So when I is 0, whatever the R that you have, it doesn't matter, V is going to be 0. So there is no potential difference between these 2 points, right? So all we can say is potential difference here is going to be equal to potential difference here. So potential difference here, we can call it V, and we can find V using the potential divider to this circuit. The potential divider E1 is the EMF or the voltage given. It's getting divided by R1 and R. So we are finding the portion of R1. And this is going to be equal to E2. So we can say is also equal to E2. Why? Because the potential here is equal to the potential here. Potential here is equal to the potential here is also equal to the potential here. The potential difference between these 2 points is equal to the potential difference between these 2 points. Right? So you can simply explain it like that again. So what we can do now is we can write by equating the 2 equations for V, E1 R1 over R1 plus R is equal to E2. So we have to subject R. They want us to find the value of R. So we have to subject R. So what you get when you simplify is fifth answer. R equals R1 times E1 minus E2 by E2. Question number 50. They're asking which one of the following circuits draw the largest current from 6 volt cell? Which one draws the largest current? So we can say largest current is drawn by the one which has the smallest resistance. So here we say if you have a resistor in forward bias, a diode in forward bias, it's lowest resistance, and if you have a diode in reverse bias, it will be the highest resistance. Right. So we'll write the resistances of each of these circuits here. So here the diode is in reverse bias, so there's no current flowing through the diode. It's infinite resistance path, so the current will go in this path. So when current goes in this path, there will be two resistors on its way. So it's 3 kilo ohms. The resistance here is 3 kilo ohms. And when you take the second one, the 6 volt battery is sending a current, but the valve here is closed. The gate is closed here, right? A closed gate, so the current cannot flow. So it's an infinite resistance path, right? Infinite resistance path. And then we can go to the next one. In that one, what we have is the diode in forward bias. So it's like zero resistance path. So the whole current goes in this way. So this 1 kilo ohm resistance is neglected. No one uses that path. If you think like if you think as the current charges as vehicles, no vehicle is taking this path because they have a zero resistance path. So it's 2 kilo ohms here. So by far this is the answer. By far, right? By far means not the answer, but by far it's the answer. And when you take this, the fourth one, the current will go in this path again. No one will use this path, 2 kilo ohm. So here the resistance is 1 kilo ohm. So by far the answer is the fourth one. And in this one, the current will get divided in both ways, right? It will get divided. So current goes in dividing because that is in forward bias. So you know when you have two resistors in parallel, the effective resistance is less than the least. Less than the least here, right? So that you know. So it's less than 1 kilo, less than 1 kilo. So this has to be the answer. Lowest resistance is the largest current. Question number 51 is asking about the effective capacitance of capacitance set. Right, here you can see there are plates connected, right? One after the other, the plates are connected to the positive terminal, and one after the other, the plates are connected to the negative terminal. So we can say directly it's a parallel system because all of the plus plates are connected together and minus plates are connected together. So we can say it's a parallel system, right? So in a parallel system, you know how to get the effective capacitance. You can just add them. You can find one and then you can add them. So let's find out how many capacitors do we have. So here, when you have two plates, you have one capacitor. When you have three plates, you have two capacitors. When you have four plates, you have three capacitors. When you have five plates, you have four capacitors. So if you have n number of plates, they say n number of plates. So we can say number of plates is n. So number of capacitors, it's n minus 1. So we can take capacitance of one capacitor as C is equal to epsilon naught A over B. So the effective capacitance, CT, we can say it's n minus 1 times epsilon naught A over B, right? So the answer is the third one. Question number 54 is about photoelectric effect. It's from methane radiation, photoelectric effect. Let's say electrons are emitted from a certain metal when monochromatic light of wavelength lambda is incident on it. H is the Planck constant and c is the velocity of light. Consider the following statement. Kinetic energy of electrons emitted from the metal is less than hc over lambda. So we have to see the correctness of this. So there is an Einstein equation for photoelectric effect where it says that the energy given by the photons, incident photons, that is HF is equal to HF. So this is the energy of a photon is equal to the work function plus the KE max, maximum kinetic energy of the electrons. Right. So the first one says the kinetic energy of emitted electrons is less than hc over lambda. So according to the equation, V equals f lambda. We can say frequency is V over lambda, V is c over lambda. So we can here write the same thing, hc over lambda equals to the work function plus Ke max. So Ke max is hc over lambda minus 5 or the work function. So we can write Ke max is equal to hc over lambda minus 5. So this is this says that Ke max has to be less than hc over lambda. So it's correct. Kinetic energy of electrons emitted from the metal does not depend on kinetic energy of the electrons emitted from the metal does not depend on the material of metal. Kinetic energy does not depend on the material of the metal. So it's wrong. Why? Because now this is the explanation for part A. So for part B, the explanation is why, because phi changes, the work function changes with the material, right? It changes. So yeah, වෙනස් වෙන නිසා කොහොමදත් K max එක වෙනස් වෙනවා. So that is the explanation for part B. For part C, let's say. So this is the wrong statement. Rate of emission of electrons depend on the wavelength lambda. Rate of emission of electrons, no, that depends on. That is also wrong. Why? It depends on the number of photons, right? So we can say it depends on the number of photons. Photons emitted or not emitted, incident per unit time. තප්පර එකකට වැටෙන photons ගානත් එක්කයි මේක වෙනස් වෙන්නේ, right? So that changes with intensity. That changes with intensity, nothing else but intensity. So the answer for this is the first one. Only A is true. Question number 55. It says a mass is attached to the lower end of a vertical elastic string. This is its neutral position. The mass is then moved downward with a constant velocity by applying a force F. So we're applying a force F. And we are moving it downwards. Right? So the tension, the additional tension, what I mark here is not just the previous tension that you had, because previously also there is a tension that you can call T1. That T1 is equal to mg. Now, currently you have mg as well as now there is an additional tension other than T1, which is T, which is because of the F force. The F force එක නිසා ඇතිවන additional tension එක තමයි අපි mark කරලා තියෙන්නේ මෙතන T කියලා. So we can directly say that T by applying F equals Kx, that this T is responsible. This T is responsible for this F. Right. It's actually the opposite. This is responsible for this T. Okay. So let's see how to do this question. They're asking the variation of time that's represented by, so we are moving this with a constant velocity. Moving this with a constant velocity. Right. So the acceleration has to be 0. So we can say that T is equal to F. T is equal to F. So there's no acceleration. So T is equal to F. And also you can say T is equal to Kx. T is equal to Kx. The extension is X. You can say T is equal to Kx. So you can say F is equal to, therefore, first we write T is equal to Kx. Current F equals Fx, F equals Kx. Now we can say F is equal to Kx. When you divide both sides by time, what you get here is the velocity and here an F and T relationship. So we can write that down as Kv T into equals is equal to. So here V is a constant, K is a constant, so these are constants. So we can say that it Y equals mx type of a graph is what we're getting here. And that is the first answer. Y equals mx type of a graph. For question number 59, we can recreate the diagram that they have given according to the scenario. It's moved towards right hand side with an acceleration e, and the length of this path is L. So here we can consider, now you know the liquid levels must be like this, right? Liquid levels must be like that when it's becoming when it's being accelerated. So this is H, and I'm considering this part, this liquid portion. So there is a pressure, and that pressure on this left hand side is giving a force on this cross section area. You can consider the liquid as a tube. දැන් මෙතන අපි කරන්නේ liquid එකෙන්ම හැදිච්ච tube එකක් වගේ කොටසක් consider කරනවා. So on that particular surface, this cross section area, there is a force that is P1A. Take that as the area as A. On this side also there is another force P2A. So we can write the pressures P1 and P2. We'll have to mark more data here. This I will mark as H, capital H, reciprocal point simple H. So P1 I can write, P1 is equal to pi plus H root G. We can write P2 as pi plus H root G. So we can then apply F equals MA to the liquid cylinder towards right hand side. So it's P1A minus P2A is equal to the mass. How do you get the mass? Is by finding volume, that is AL into rho into A. So here you can see A's are getting cancelled on both sides, P1 minus P2. So when you deduct P1 minus P2 from P1, what you get is simple H rho T equals L rho A. So rho is also getting cancelled here. So A, therefore H not A. It's LA over G. That's the answer. Question number 60. So here, if you have read this question, you know what it says. We have a wireframe like this. That's this shape. And on that wireframe, we have another wire which can slide. And that is sliding on that wire to the right-hand side with a constant velocity. So this triangle will become always an equilateral triangle because this angle is 60. Both of these angles also must be 60. So they are asking when it is moving towards this side, what is the variation of current in the circuit? Or how would that vary? The current, variation of current. They're asking how the current would vary over time. Right. So here we can first mark, or we can just find out who is making an EMF. So this part is moving towards right hand side. So that part is the one who's making an EMF. So we can use the right hand rule. So movement is towards right hand side, magnetic field is into the plane, and then the current should go upwards. So in order to do that, the EMF should be like this. So there will be a current like this. So this current depends on the EMF, and that EMF must be the EMF made only by this part of the wire. මෙන්න මේ කොටසෙන් හැදෙන EMF එක විතරයි ගන්නෙ wire එක මේ පැත්තට දිග වුණා කියලා ඒ ටිකෙන් හැදෙන EMF එක මේ current එකට effect වෙන්නේ නැහැ. Right. So we only take the EMF created by this part. So that you can say the L is the length of one part of this frame. So you can say L. So if the resistance, okay, we will write directly the equation for the current. Getting the equation current. So the current is E over 3R. What is R? R is resistance of one of the sides. So we can say R is equal to simple R into L. So what is simple R? Simple R is the resistance per unit length. Resistance per unit length. Right? So what is R then? Sorry, L. This is L. The length of the wire is L. Right. So we have marked all the data now. So when it says 3R, it's 3 times RL. And you can also apply E is equal to BLV to the rod. Rod diagram equals BLV dana. So it's E equals to B into LV. So that's BLV as it is. So V the constant. So now it's the time to apply. E is equal to BLV divided by 3 times R into L. So here R gets cancelled. Sorry, L gets cancelled. So what we get is BV over 3R. So here, the thing is, V is a constant value, doesn't change with time. And also, they have given that V is a constant. R is resistance per unit length, a constant. So is anyway a constant, you have to take a constant. So it's a constant. I is constant, so it does not change with time. So what is meant by constant is that it does not change over time. The current does not change over time. So it's a constant value. Current එක වෙනස් වෙන්නේ නැහැ කියලා මෙන්න මේ විදිහට තමයි අපි පෙන්නන්නේ. Right? So you have to understand that this is the way that we have to explain. You just can't say at once that the current is constant. එකපාරටම current constant කියලා කියන්න එපා. එහෙම කිව්වොත් වැරදි. So you have to prove it with facts and figures, right? So here we have proven that the current is not changing using the facts and figures. හරි විදිහට proof එක පෙන්වන්නේ මෙන්න මෙහෙමයි. Right. So this is the end of the discussion of 2001 paper. Here the questions we have discussed were 22, 23, 35, 39, 48, 50, 51, 54, 55, 59, and 60. Thank you.